Okay, so for this chapter itself, this is your first chapter on electricity. So we're going to learn about your different components of electricity and what actually is electricity first. Okay, so we're starting on this chapter called static electricity first. So what is an electric charge? Now, electric charge, right, basically is just a basic property of your metal itself. It's just something. Okay, so basically there are two types of charges. So we have your positive charge and your negative charge itself. And your charge, normally we represent it with a letter Q. So your charge usually is Q and you have a value, and then you have your units, which is actually called coulombs. Okay, now this line over here, okay, there is one part that is wrong. It is not an atom, it is your electron. That is your smallest particle. Why? Because your atom is electrically neutral. Because your protons and your neutrons, your protons and your electrons, they are charged, will cancel each other out. Okay, so the smallest possible one is just your electron itself, where you have a certain value. Now, you don't need to worry. You don't have to memorize these values. Okay, in most questions, they actually give it to you if necessary. If not, they won't actually use charge very often. Charge is one of the quantities that's very rarely used, but it's just one of the few like fundamentals itself. It's kind of like, you know, particles that make up like make up your whole entire structure and stuff like that. It's like we know it's a particle, but we don't really go into depth about like describing what a particle is. Kind of logic. It's like, okay, so the same holds true for your electric charge as well. You just need to know that electric charge is this. It holds a positive and a negative value. And for your charged object itself, you have three different types. You have the neutral or your uncharged particles. You have the same number of electrons and protons. So if you ever forget, electrons are negative, protons are your positive. Okay, so your negative and your positive. So because they have the same number, they will actually cancel out. And on the other hand, you have less electrons and you have more protons for your negative charge and your positive charge. Okay, and if you notice, I put my electrons on the left-hand side. Every time we phrase it, it's the number of electrons that is more or less than your protons. It is there for a certain reason. Okay, so before we move on to that part about all your charge itself, we need to identify your force. Okay, so if you recall back to your dynamics itself, we learned about your non-contact forces, your gravitational force, your electrostatic force, and your magnetic force. So in this case, this electric force or electrostatic force is what we are talking about. It is a non-contact force. So what's the property, or how do you have this force? How do you know which direction that you're moving at? Is like charges repel. So if you have positive, positive, they will repel. If you have negative, negative, they repel. But if you have opposite charges or unlike charges itself, they actually attract and move towards each other. And like all your non-contact forces, as distance increases, the force will actually get weaker and weaker as your distance increases. Okay, so if you notice, you have two forces over here. You have force 1 and you have force 2. These two are your action-reaction pairs. Because if you recall back, they are the same type of force. Both of them are electrostatic forces. They have the same magnitude. They have opposite directions, and they both act on different objects. So this is your action-reaction pair. Same for this, same for this, same for this. All of them are action-reaction pairs. Okay, so moving on. So because of your non-contact force, so actually for non-contact forces, all of them will have a field. So if you recall back to your dynamics, when we learned about gravitational force, there is a gravitational field. Same thing for your electric force and your magnetic force. Same thing. All of them will have their own fields as long as it is a non-contact force. So definition that you need to memorize: electric field is a region in which an electric charge experiences an electric force. This part you need to memorize. Okay, so for your fields, we can represent them with arrows itself, and you will notice that the direction of this part, the direction of your electric field will be where your electric force acts on a positive test charge. So what exactly is a positive test charge over here? Okay, it's just a very, 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 very small and insignificant positive value. Okay, so you can just imagine as this is a theoretical charge that if we place it, for example, if you place a positive here, what happens? Unlike charges will repel, right? This one will move back. But because your positive charge is so small and insignificant, it doesn't affect my bigger charge over here. So it doesn't affect it. So you can see the direction of your repulsion will be away in this direction. If you notice, though, all of them are straight lines because there is nothing that is affecting it. So they'll just move up, down, left, right diagonally. Okay, and keywords is basically your field lines will always be from a positive to a negative. So you can see itself, if I place my positive test charge here, it will move towards the negative. So you can see if I place it here, it will move towards here. Basically, that's what it means. Okay, so because field lines are, your electric field lines cannot be seen with the naked eye. It cannot actually be seen. So the only way that we actually managed to deduce this was to actually just grab a positive test charge and place it right beside your isolated positive charge and your isolated negative charge. These two are separate. So now, if these two are separate and they all draw straight lines, what happens if we have two different charges? So you have a positive charge, you have a negative charge. You can see that lines will move from plus to minus, and you notice the lines are now going to be curved. So apart from the horizontal lines, the rest are all going to be curved now. And if you see this point here, they are going to be symmetrical about this point. So as much as you can, try to draw it as symmetrical as you can. Looks kind of like a spider. Okay, and if you recall your gravitational field, we also learned about gravitational field strength G, correct? So, but for electric field, we don't really need to do so. Basically, the closer you are, the stronger it is. Okay, so closer field lines equal stronger field, equal stronger force. Okay, so basically, the closer you are, the stronger the attraction and the stronger the repulsion itself. So if you notice, this part, the lines are very, very close, right? But if you compare it to these few lines, the lines are further apart, correct? So you can see that the lines nearer to the charge itself will actually be stronger because remember, electric force is a non-contact. As your distance from your charge increases, your electric force will actually get weaker. So just take note, the further you are, the weaker it is, the closer you are, the stronger it will be. Okay, so do take note. And if you have two positive charges over here, they actually repel each other itself. And if you do have two negatives, what happens is that the shape will be exactly the same, just that the arrows will now be inwards. Okay, so you want to draw a roughly 5 to 8 lines, and you should try to make it as symmetrical as you can. Okay, as symmetrical as you can. So basically, you'll notice that yes, this middle part will still be empty as well. Just that now everything is exactly the same. Apart from your arrows itself, it should be inwards, towards negative, away from positive and away and into your negative. And very important line here is your lines do not cross. Once you cross, -1 mark straight away. So your lines can never cross. You should always make sure that they are as symmetrical as you can. Okay. So next part, let's do some work examples so that it will be easier for you to understand. So first things first, you have your charge plates. Okay. So now, charge plates itself, you can just imagine plates are just your metal, like thin metal pieces, right? And then you have 4 particles. Now these guys are very small. Okay, whereas your plates are very, very big. So they are going to be more significant. Okay, they are more significant itself. So in part A, how are we supposed to draw your electric field lines between your plates? Is you grab a ruler. What you want to do is, because your two plates are much bigger and much more significant compared to small little particles, right? So you can just imagine your metal itself, your amount of substance is made out of small little particles, so your particles are super duper small compared to your solid metal plates itself. So what you want to do is at the two edge, you want to draw straight lines, and in the middle, you draw straight lines, and basically in between both, draw straight line, in between both, draw straight lines. Do take note, the spacing between your lines itself should be roughly the same, because you want to tell the marker that the electric field strength is roughly the same throughout. Okay, so if you draw it properly itself, it should look something like this, and you will notice the field lines will be moving from plus to minus. Okay, so what's so special about your field lines for your metal plates is that they have the same electric field strength between the plates. Okay, so now on a side note, if we don't draw between the plates, what about the edge over here? If it's the edge, it will curve. Okay, and because you curve, your distance, right, is no longer the same. You actually are further apart. So the magnetic field strength at the edge will actually be weaker than the ones inside or in between the two metal plates itself. Okay, so do take note, you only need the red color part, the blue color part is for understanding. So if you introduce this for negatively charged particles itself, what will happen to them? And they will basically move towards the positive side, because unlike charges will trap. Now, which of the particles will experience the same force? Keyword, due to your electric field. Okay, so if you notice your electric field, all of them are equally spaced apart, which means no matter where you are, as long as you're between or within this magnetic field, all of them will experience the same force. So the particles P, Q, R, and S all experience the same force. Okay, so they all experience the same amount of force because the electric field strength is exactly the same in your metal plate. Okay, so you might want to say, some students be like, sure, doesn't the distance between the distance between the particle and the plates matter? Yes, but the thing is, the particles are much, much smaller compared to your metal plates itself. So we will base it off your field lines rather than your distance itself. Because if you want to talk about distance, you can see from here, if your distance from your plates are significant enough, you will show a difference, right? The distance is bigger, this part is stronger. But because your plates are so big and so strong compared to a particle itself, they are uniform inside. So because they're uniform inside, they actually have the same amount of electric force acting throughout in between the plates. So because of this, P, Q, R, and S, even though they are spaced, P and Q is nearer to the plus, they all experience the same amount of force. So the difference will be quite insignificant. So we just take according to the field lines. Okay, now next one. So same thing, always read your questions carefully. You have positive charge, and this is the direction of your field. So this is positive, this is negative, because we always move from plus to minus. So what is the direction that your positive charge will move? The positive charge will move towards E. Where would it move? It will move downwards. Or you can say that it will be deflected downwards. Okay, why is that so? Okay, so first thing is, since like charges repel and unlike charges attract, the positive charge will be repelled away from the positive it will be repelled from the positive charges at the top. and be attracted towards the negative charges at the bottom. Okay. So do take note, because you are in an electric field, don't forget, going back to the notes itself, right? Your electric field will always point away from a positive charge and towards a negative. So because of this, on top is positive, below is negative. How would you draw this? Is you grab a ruler. So before you enter, you will still travel very nicely in a straight line. Okay? But once the moment you enter, you will actually like this. Okay, so because of this, you actually be deflected downwards. And if you are not moving fast enough, you will actually end up just moving downwards itself. If you move fast enough, you might still be able to escape from your electric field. And at this point, you will just because there's no more deflection, you will just travel in a straight line afterwards. So there's three parts. One, straight line. Middle, you start to bend downwards, and then this part, if you escape it, you will manage to go out. Now, but if you don't manage to escape it, like just now what I drew, is that you will just end up being inside the electric field. And if there is a plate, the positive charge might just end up touching the negative plate on the other side. Okay, so that will be all for the electric field parts. All your electric charges, you need to know what they are. All of this, your electric force, your electric field patterns, your electric field strength, and all your metal plates and your particles itself, how are they interacting with one another? Okay.